Morning, everybody. It's time to start today's morning session. In this session, we have three. We will have three lectures. Yeah, first, Jiajun Wang from Peking University. He is going to talk about the minimal length of non-simple closed geodesics on hyperbolic surfaces. Yeah, please start.
Okay, thank Professor Senodi for his introduction. Also, I would like to thank the organizing committee, especially Professor Nikolai Ambosimov for inviting me to give a talk here. So I will talk about minimal length of non-simple closed geodesics on hyperbolic surfaces. So first, I want to recall the classical color lemma. It says that so if we are given a hyperbolic surface, so we'd better suppose it's geometrically complete. So if we have a closed geodesic, so then it will have a neighborhood which is embedded annulars. So where so the annulars consists all points. So with distance from this geodesic with less than WLC. So where W is given by this function. So because we need to analyze this function, so we want to simplify this function. So we see that this is larger than the log of 4 over x. So here, so we are using the logarithm of the e, so the natural number. Okay, so given this color lemma, so we can give this surface classical thick-thin decomposition. So where if you have this geodesics is tubular, so its neighborhood, so given by the color lemma, which is annulars. So now the rest part will considered to be the thick part. So the thin part are just a bunch of annulars. So we will mainly consider a metric incomplete hyperbolic surface of finite type. So actually it also works on a hyperbolic surface with geodesic boundary, but so that's just so a little corollary of that. So we mainly work on the metric complete part. So for the non-simple geodesics, so first we have the results of Yamada, so in 1982. So his conclusion is that, so the length of non-simple geodesic, so in a closed hyperbolic surface will have universal lower bound, so which is 4 log 1 plus square 2, and this lower bound is the best. So namely, if you have a geodesic, so if it has length less than this number, so then it has no self-intersection. So this is his result. So Hempel then so then this for a complete hyperbolic surface, not necessarily a closed one. So then a loop less than 2 log 1 plus square 2 is homotopic to a power of simple loop. Of course here, so it does not suppose this is simple. So anyway, it could be a multiple of small loop. So Yamada is result. So actually, so this is an example where it reached this bound. So this is given by a pair of pants, which is ideal. So all ideal pair of pants. So then you start with this point. So of course, this is not, so the middle point does not make sense here. So it will have same length from this point to the other edge of ideal triangle. So then you get perpendicular, so geodesic from this point to the other edge. So then we glue 2 copies of this. So we'll get a closed geodesic. and it will have a length of 4 log 1 plus square 2. So then this is the smallest closed geodesic with a self-intersection. So now we ask the following question. So can a closed geodesic with bounded length have arbitrarily many self-intersection? So in a way that, so for example, of course we can allow this number to be bigger than so the lower bounds of Hempel and Yamada. So can we have arbitrarily many self-intersection? So of course we need to give a definition of self-intersection number. So as so closed geodesic, so if it's non-simple, so it's not necessarily so of general in general position, so in the topological sense. So we give the following of this definition is given by Basmanjian. So suppose we have a closed geodesic, so that means then we consider all its double points. So that means we have two different points on the circle, so then their image is the same. So this is, so we not only have double points, we could have triple points or more than that. So we consider all this, the pre-image of these points. So if its number is n, so we consider it's n choose 2, a number of self-intersection. So of course, this we can also consider we can perturb this this geodesic in general position. So then we will have n choose 2 number of self-intersections. So then we add all this. So we call this the self-intersection number of this closed geodesic. So this will be the precise definition of self-intersection number. So of course, a non-simple closed geodesic, so it will have such number. So you want to control the length. So control the length of this, so for a closed geodesic with k self-intersection number. So give a lower bound for that. So Basmanjian have this result in 1993. So give a number, a positive number k, then there is a lower bound of length of closed geodesic of self-intersection number more than k. And this bound depends only on k. So this means that, so the length of a closed geodesic will get arbitrarily large when its self-intersection number gets large. So it's bounded below by a function, so which approach infinity as k gets to infinity. So the way he get this is he defined a stable neighborhood of such a geodesic. Now, so now we want to consider, so the k geodesic. So by a k geodesic, we mean a closed geodesic with k self-intersection numbers among all hyperbolic surfaces. So namely, we do not fix the hyperbolic structure. So we will consider all such hyperbolic surfaces. We want to get the infimum of the length of k geodesics. So of course, this should be positive. So given Hempel and Yamada's lower bound. So the infimum is taken. So then Barrybot in 1999. So he showed that for any epsilon positive, then we have this mk is less than 2 plus epsilon log k for k sufficiently large. So this means that, so given not any number k, of course with this epsilon, so then we can find a closed geodesic with self-intersection number k, so that its length is less than 2 plus epsilon times log k. So this is obtained by analyze length of such simple closed such closed geodesics on a pair of pans. So he computed, so essentially all the length of closed geodesic on a pair of pants, and he showed that in the ideal pair of pants, so the length gets the smallest. So then he gets this upper bound. So to get the upper bound, we only consider a particular hyperbolic surface. But to get the lower bound, so we need to consider all hyperbolic surfaces. So as mentioned, in 2013, he showed a stronger result. So if we fix the hyperbolic structure, so then the length of closed geodesic of self-intersection number k, it will be less than c times square root of k. So, and this constant related to the surface depends on the topology and the hyperbolic structure of the surface. Thus, so if we fix this hyperbolic surface, so then Erlandsen and Collier in 2020, so then consider the following question. So we consider all closed geodesics with at least k self-intersections. So we consider the one with shortest length. So then the self-intersection number of that shortest geodesic, so they denote by this AKX. So X is a hyperbolic surface. So then this is bounded by a function depends only on k and grows linearly as k gets large. So that means, so this number is less than so some number times k. So they should also show if the surface have at most one cusp, so it is either closed or has at most exactly one cusp. The ratio of this AKX divided by k is asymptotic to 1. So they also make a further conjecture that this is a case for all orientable complete hyperbolic surfaces. So whereas the bounding function it will be 512 times k. So these are the results for a surface with fixed hyperbolic structure. So now, so as mentioned in the same paper, so he showed a result that, so this MK, so of course the upper bound is also given by Barry Bob. So he showed that this is larger than half of log half of k. So this is the lower bound. So roughly speaking, so this on the left and on the right, so they are also on growth rates of log k. So this symbol means so these two, the quotient of these two is bounded below and above by positive number. So what we are going to do is analyze exact growth rate of this MK. So let sigma be a hyperbolic surface. So, and we consider a closed geodesic on that. So suppose its length is bigger than 4 times log 1 plus square 2, so then it could be non-simple. So we will represent the closed geodesic by a local isometry from a circle of length L to the surface. So the question is this. So what's the upper bound of the self-intersection number for a closed geodesic in a hyperbolic surface which length smaller than L, or we can see equal to L. So by the result of as mentioned, so this self-intersection number cannot be arbitrarily large. So if the length of the geodesic is fixed. So what we will prove is that, so let M be the infemoral length of K geodesics. So means closed geodesic with intersection number k. So among all metrically complete hyperbolic surfaces of finite type, so then actually mk divided by 2 log k will equals 1. So it means mk will have so Greece rate 2 log k. So which is the same as so the right hand side of Benjamin's result. So what we are doing is the following. So we consider so a closed geodesic with length L. So we show that so the self-intersection number of this closed geodesic will less than 9 times L squared times e to half of the length. So so we write this as a metrically complete hyperbolic surface. So it also works on closed on a surface with geodesic boundary. The reason is because if we have with a hyperbolic surface with closed geodesic boundary, so we can double the surface to get a surface so with no geodesic boundary. And if it's finite type, so the double of that is also a hyperbolic surface with of finite type. So we allow the hyperbolic surface to have holes. So which means it has a closed geodesic. Its length bound to goes to infinity. So it has a large hole of that. So this also okay. So here this none. The reason we use none here, it works on L. It's bigger than 4 times log 1 plus square 2. So if we let the length to be very large, so it's possibly to get 8 plus epsilon times L square times e to half of the length. So symptotically, so so the upper limits will be 8 L squared times e to half of L. So so this is our result. So now I want to talk about a little bit about the idea of this proof. So suppose we have a constant length which is bigger than that. So this will be bigger than 3.5. So we consider so here could be a metrically complete surface. So don't necessarily to be closed, but here we mainly talk about the closed case. So we denote the length of a curve by LC and let X to be the collection of closed geodesic on the surface with length than its length less than e to minus L divided by 4. So because this L, so it's bigger than this number, 4 log 1 plus square 2. So then such geodesic will have less than 0.42. So note that this depends on so the length of the closed geodesic we are considering. So if we consider the so it's closed geodesic of length so sufficiently large, so this X could be empty. So because so this number, so it's less than so Hempel's universal lower bound for non-simple closed geodesics. So apparently, so curves in this X will be simple. So now I want to rewrite this color lemma and to get neighborhood of that. So then given curve in this X, so we consider the neighborhood where so it's length for points with length less than this WLC of this curve. So this WX is given by the color lemma. So then it's not hard to see that geodesic in this X are disjoint. So now we want to define several neighborhoods of that. So the reason we will change this a little bit is because this function is not easy to analyze. So we want to consider all points with distance to L less than log 1 divided by the length of this LC. So suppose this X be this number. So this could be this X could be empty. So now we want to make sure that the distance of this N2 neighborhood to the boundary of the N3 neighborhood is about a quarter of the L. So now we get this N1. So this length is nearly a quarter of L. So this is a quarter of L. So the reason we consider this is, if we have a closed geodesic of length L, so if it intersects with this N1, so then it cannot go out to this neighborhood. So then we get it either, so if it's closed geodesic, it has to be a multiple of this Ci. So then it will not be a closed geodesic. So it has to be the Ci, it will have no self-intersection. So this is the motivation for defining this neighborhood. Of course, so because this L, so this number, the log of 1 over the length of Ci, this is fixed. So this L could be so arbitrarily large. So when L gets very large, so either this N1 or N2 neighborhood could be empty. So now I talk a little bit about cusp case. So it's a result of Adams says that so if we have cusp, so it will have a maximal cusp where the length is or the area of the cusp is at least 4. So the lower bound 4 is realized on an ideal pair of pants. So now, so this means that this any puncture of the sigma or cusp of that, so it will have a cusp where the length of its boundary is equal to 4. So this so that means every cusp has such a neighborhood, so that its boundary length is equal to 4. So now, so suppose this one is equal to 4. So the length of this. So when consider, so this is the 2 log 2, and this part will be 4 times L. This is 4 times L. So for cusp case, all the neighborhoods are not empty. So we will, so all this, so in the cusp case, so all the neighborhoods will play the same role for the short geodesics in X. So these are the neighborhoods we are considering. So we want to analyze the injectivity radius. So let A be an annulus. So in the surface with boundary circle gamma 1 and gamma 2. So where one of them, so gamma 1 is a closed geodesic, and gamma 2 is a piecewise smooth. So actually it works for it's rectifiable. So suppose that there exists some points so in the gamma 2, so that its distance from gamma 1 is d. So then the length of gamma 2 will really the sine hyperbolic of the half length, so we will be bigger than 4 or quarter of each d times the length of gamma 1. So this is just standard application of the Lambert quadrilateral. So if we have this length smaller than d, so then we have the length of gamma 2 is bigger than 25, so 12 over 25 times e to the d times L gamma 1. So this is because this number is very small. So we can remove this sign hyperbolic to get number here. Okay, so now we show that for two distinct geodesic, closed geodesic in the, or we call the short geodesic. So there are N3 neighborhoods are disjoint. So this is just if their N3 neighborhoods are not, so they are not disjoint. So then we can apply this result to show that their length will be bigger than so the lower bound we have here will be the lower bound than here. So all the N3 neighborhoods are disjoint. So now we will give a thin thick decomposition of the surface. So we will call N1 to be the union of all this N2 neighborhood of the short geodesic. It also includes the case so where Y is the set of cusps. So then this will be the thin part, where the rest will be the thick part. So we note that the thin part is, so actually this is open and this is closed. So this decomposition is different from the regular thick-thin decomposition. So because it depends on the constant L. So it's the length of the geodesic length where we are interested in. Okay, so now so we can prove that so the injectivity radius of the thick part, so it's bigger than this. So or we can say the sign hyperbolic of the injectivity radius is bigger than this number. So because our length is bounded below by 3.5, so this will be bigger than 25 over 101 times e to a quarter of L. Okay, so now, so as I said before, so the geodesic of length L will disjoint from so the N1 neighborhood because so the N1 neighborhood, this is the boundary of N1. So it has distance to the boundary N3. So the length here is roughly speaking is 1/2 L. So if it intersects with N1 neighborhood, so it cannot go out the N3 neighborhood where, so the N3 neighborhood is annular. So it has to be a multiple of this curve. Okay, so now, so the next, proposition is show that so it disjoint from the N1 neighborhood, but it could be it's possible it intersects the N2 neighborhood, but we show that it can only intersect a single N2 neighborhood. It cannot intersect two of them. And in case it intersects with the N2 neighborhood, so it is connected, and namely it's an arc. So now, so we consider, so the gamma is the interesting closed geodesic of length L. So we divide it into two parts. It's in the thin part and in the thick part. So in the thick part, so it's an arc. So the rest is in the so the thin part is an arc. So it's also, so the thick part is also an arc. So now, because these two parts will not intersect, so the self-intersection number of gamma will be the sum of the self-intersection of the two parts. So now there will be three cases. So the first one is, remember, gamma 2 is the thin part. So it could be the case that the thin part is empty and the whole curve will disjoint from the N2 neighborhood of all short geodesics and cusps. So this is a simple case. So the general case, it will intersect a unique so N2 neighborhood, and then so the curve is go like this. So if we look at it in the universal cover, so this curve will be a geodesic, and this neighborhood so this is the C1. So in the universal cover, so this neighborhood it look like this. The N1 neighborhood. So then the interesting geodesic will first go from here, and then like this. So it will intersect with this N2. So this will be the case in the universal cover, and this is the general case. So here, so it could be a closed geodesic, and also could be a cusp. So then in a cusp, so if we consider the cusp to be the infinity, so then this will be the N1 neighborhood, right? So this is the infinity cusp, and this will be N2. So then the geodesic will look like this. So this is the cusp case. Now we also have the special case. So this is a case where so the N1 neighborhood of some curve Ci is empty, and this curve could be go from one end of the N2 neighborhood and goes out from the other end of this N2 neighborhood. Of course, this in this case, so it does not occur in the cusp case because so you cannot go. If you go to the cusp, then length will get to infinity, right? So this only occurs for the short geodesic case, not for the cusp case. So then what we do is, so we compute the so the self-intersection number. So in all the three cases, in the thin part and in the thick part, because the path in the thin part, so it's analyzed, so we can actually compute according to so the injectivity readers. So let's first consider the thick part. So the thick part is see it's operating by this. So we showed that so in the thick part, the injectivity radius is bigger than this number. Right, it's bigger than this number. So now what we do is this. So we divide, so it could be arbitrarily complicated in the thick part. So we divide this curve in small pieces. So where the length is equal, is a little bit smaller than the injectivity radius. So the idea is that, so if we have two such piece or segments of less than the injectivity radius, it could intersect, but the intersection number is at most one, right? And most one, because so if this is a short geodesic segment of less than the injectivity radius, this is this two. So if we get this part, so then we get contradiction, because from this part, so the injective, so from this point, so so the injectivity radius is bigger than the length of this, right? So it should also only have one intersection. So this is a basic idea. So for the estimate of the intersection number in the thick part. So that means I will repeat again. So if we have two geodesic segments with length less than the injectivity radius, so it has at most one intersection. So now we will divide this into this is actually so the quotient of L1. So by the injectivity radius, we take the integer and we plus one. So we divide this into such number of closed segment. So we want to make this closed segment because the intersection could happen at the ends of this segment. Okay, so now because any two segments has at most one intersection, so then we can choose two, right? Suppose we have m number of closed geodesic segments, so then we have at most 1/2 m times m minus 1 number of intersections. So the self-intersection of gamma 1 is at most this many. So of course, this does not look beautiful, but because we want this apply to any length, so we get this ugly estimate. So this is the estimate in the sig part. So now in the sin part, so it's nearly the same. So the reason is because, so we consider it's the smallest possible injectivity radius. So because it goes like this, so symmetrically it has points here. So we like this x naught to be the one closest to so the left of the closed geodesic. So this is in the universe cover. So then the intersection points are symmetric so to this number, right? So then the idea is this: the length of this is bigger than the twice the injectivity radius, and this also will be larger than the, so twice of this is bigger than the injectivity radius, twice the injectivity radius. So all this will be bigger than the injectivity radius, right? So we get the intersection number bounded so by the injectivity radius and also the length of this sig part geodesic. So now this is bigger than that. So this is twice the injectivity radius. So we get that. So this L2 is bigger than this this, right? So the self-intersection number times the length so of smallest possible so curve. So then we get this estimate. So now we will add these two intersection number together to get the upper bound of intersection number. So we prove that the self-intersection number of closed geodesic on metric complete hyperbolic surface with length L is less than 9 times L squared times e to half the length. So if this length is very small, by Yamada, it has no self-intersections. So this holds automatically. So for length bigger than this number, so we will analyze this function. So it's actually just you have a couple of functions to analyze. First, you get this, and then you will get for L bigger than 2.5, so a smaller than 9 times L squared times e to half of the length. So this is the estimate of the self-intersection number. So now what we do, what we need to do is just want to reverse this process to estimate the length by the self-intersection number. So it's actually just so the derivative for some functions. So the corollary is this. So if for any closed geodesic with k intersection number, so it will be bigger than 2 minus epsilon log k for k sufficiently large. So for any epsilon, so positive. So I will just write the proof here because it just uses the derivative of certain functions. Okay, so combine this corollary and the result of variable, we show that mk. So variable show this this is smaller than 2 times epsilon log k, right? So then Then we show that as k goes to infinity, so the quotient of mk and 2 log k will be equals to 1. So the growth rate will be 2 log k. So I want to make a further remark that, so we can know, so if you want to have, so most intersection, so where is the intersection appears? So then, so where it has most self-intersection, so it actually appears in the neighborhood of a closed geodesic or a cusp. So just as in the general case. Just in this case. So this is where you could realize as so most intersections. So it's so outside the N1 neighborhood, and we can show that. So, but this is not relative to the main result. So if we let this to be the N3 neighborhood, we let this length to for N2, so it will be half of the length, right? If we have 3 of the L, then most intersections will appear in this area. So this is the idea to get the most intersections. So with a given length, so it will appear in the neighborhood of a cusp or short geodesic. Okay, so this is all we get, and maybe I stop here.
Thank you, Professor Wang, for your interesting lectures. Are there any questions or comments? Questions or suggestions or other comments?
It seems there are some questions in chat.
Yeah.
And let me look at them.
So no questions?
Oh, so this sigma, not sigma g, but that's the same. It seems that call diagram of node can apply to non-simple closed geodesic here, and counting intersection is just counting calls. So it could be. So actually, what we are doing is we
Professor
are
Wang,
also,
we can see your sheet because
okay.
yeah, it is small. Yeah, please.
Okay.
Yeah.
Okay, so this question is says use the call diagram of a node. So I'm not sure whether so this could be so it will give
okay.
give a shorter proof or a better proof. So but we are doing in the SIG part is nearly the same. So we separate so this curve into some small segments and try to count so the intersection between all these small segments. Maybe the idea is the same.
Okay. Other questions or comments? There are no more questions? Okay, then thanks again, the Professor Wang, for his excellent lectures.
Thank you.